Okay, so for this lecture, I'm going to talk about arrangement of electrons, or working up to electron configurations. So we talked about how the atom is arranged as far as where protons and neutrons and electrons are generally, protons and neutrons being in the nucleus and electrons being out in this cloud. But what we really want to know is how are the electrons arranged out there? So what sort of configuration are the electrons taking? And the question you might come up with, or it might be reasonable to ask at this point, is why do we care? Why is it important to know what the electrons are doing? Isn't it enough to know that they're out in the cloud? Well, the answer is if you think about the way the atom is arranged, right? You've got your nucleus here with all the protons and neutrons and all that done here in the nucleus, and then you've got your electrons out here in this cloud. When two atoms come together, right, what part of them actually interact? The answer is it's the nucleus. Not the nucleus. Not the right answer at all. The answer is it's the electrons. The electrons are what actually interact, right? They're what bump into each other. So all of the chemical reactions and processes that we see and observe in chemistry are due to the electrons. All about what the electrons are doing. How are the electrons moving between atoms, and how are they shared between atoms, and everything having to do with electrons. So all chemical reactivity has to do with electrons. The nucleus doesn't really change except for in nuclear processes, which is kind of outside the scope of what we're going to talk about. All chemical processes have to do with electrons. So really, it's the electrons that dictate all the chemical properties of the elements. Even really the physical properties, because they're just sort of outgrowths of how the electrons are arranged. So, all right, so let's talk about how electrons are. So, a guy named Niels Bohr first came up with the first model of how electrons are arranged. And so what was already known before Bohr was that the electrons were in constant motion. They have some sort of kinetic energy. They're moving around very quickly out there in the out in the electron cloud. What he discovered is that this energy is quantized. Now, quantized means it can only come in discrete, certain values, right? This is kind of a weird idea. The idea of, but it's very much akin to atoms, right? The idea is that energy can only be transferred in certain units of energy, as far as electrons are concerned anyway, right? So if my car was an electron and I pushed on the gas, it would instantaneously jump from going 0 miles an hour to maybe, say, 10 miles an hour, right? And it's never allowed to go any speed between those, right? It's basically infinite acceleration, right? You just instantly jump, right? Well, this seems really weird and bizarre to us, the idea of quantized energy. But if you think about it in terms of atoms are quantized matter, right? If you get down to the smallest chunks of matter, there are these discrete, separate pieces of matter, right? Well, why does matter then not really look like that to us? And that's because the pieces, the atoms, are so small. Well, in the same way, this energy is so small that we don't notice it, right? But it's really important for electrons. It's also important to know that the lowest energy configuration is what's called the ground state. And from there, Bohr said, he came up with a lot of other things that I'm not going to go into, but he described electrons as having specific orbits. So he described the protons, and then there's an orbit, there's an electron here, and another orbit, and here. And he said each orbit has a specific energy, right? So an electron can jump from one orbit to the next and to the next, or back down again, right? And it never orbits in between. And so this is why there's specific energy. It's only allowed to be at certain orbits. So he was partially right. It was found that they don't orbit the nucleus like planets around the sun. Instead, well, then you might say, well, smarty pants, what is it they do? And my answer would be, we don't really know. We can't really know. Because to follow where something is and what pathway it takes, you have to be able to observe it all along its pathway. So let's take a moment and talk about what it means to observe something. When I'm up in the front of the class lecturing or talking or doing problems or whatever, how is it that you can observe where I'm pacing around, right? Well, the answer is I'm walking around the classroom and you have a source of light. And you're bouncing light off of me, right? And that goes to a detector, which is your eye. Big creepy eye that I just drew. Now, if you did the same with an electron, right, and then try to bounce it to some sort of a detector, well, there's a bit of a problem. Because electrons are really, really, really small. The energies that they have are really, really small. So this would be more akin to trying to figure out where I am by throwing bowling balls at me. And yes, I'm saying this to be comical. The problem is, you really get one of two results. Either I would duck out of the way, thus ruining your ability to know where I am, right? Right? I keep going in the same direction, right? But you wouldn't be able to know where I am. Or, sorry, bowling ball goes over my head. Or you would successfully figure out where I am by bouncing the bowling ball off of me. But whatever trajectory I was doing, I am now not. Seeing stars. Right? So I'm no longer going in that particular direction. I have been knocked down by a bowling ball. So I'm being hyperbolic and funny with that, but the idea being that if you hit an electron with a ray of light, that ray of light conveys so much energy to the electron that you change its orbit. You disrupt what it's doing. It goes careening off in some direction. And so the best we can do is do this, is to ping it over time. So we have our nucleus, and then I take a sample, and I can never figure out the pathway the electrons are taking. But I can figure out where an electron of a particular energy tends to spend its time. Right? So now I get a picture of the electron as a map. Now, it'd be much more dense and a lot more data points than that. But you get these little images of where the electron is, and you get these little spaces so you can get an appropriate energy and an idea of where it is. So we're not going to talk about orbits. We're going to talk about these regions of space where the electrons tend to exist. And they're called orbitals. So they're called electron orbitals. Right? And orbitals are just the region of space where the electron is. Well, we actually have to describe them. We can describe each orbital in sort of a categorical way. What we're going to do is we're going to start from the most general and get to the most specific. So orbitals are where the electrons live. So electrons, and we'll talk about how many can go in an orbital in a little bit. Oops. I don't know why I'll just draw it again. So how many electrons can go in an orbital? Electrons can go in orbitals, and in a subshell, there are several orbitals. We'll talk about how many. And in a shell, there are several subshells. Again, we'll talk about how many. But this is just getting more and more specific from shell to subshell to orbital. So you can really think of this like trying to find an address, right? Most general term, shell, is akin to like city, what city you live in. Subshell is like the street, right? More specific, in a city there's lots of streets, and on a given street there's lots of houses or house numbers, so the orbital is the house number. So we're getting more specific, right? So the most general, I'm going to start from the most general and get to the most specific. Now there's going to be a lot of jargon and a lot of things, but just realize what we're doing is we're just trying to describe, we're trying to categorize the orbitals, because there's lots of them, and I'm just trying to categorize them in a way that makes more sense. So the broadest category is shell. Now, in broad terms, the term shell describes the energy and location of the electrons. So what I mean by that, first we're going to describe them with n numbers. N equals whatever. So to describe a particular shell, I refer to a specific n number. N equals 1, 2, 3, 4. And they can go all the way up to infinity. We're generally not going to get much higher than like 7 or 8. And really most of the time we're going to stay in the 3, 4, 5 range. But higher n indicates two things. Higher energy. So an electron in n equals 4 has higher energy than an electron in n equals 2. Now, as I said, we're not all the way to describing yet. In n equals 4, there's lots of different orbitals. And in n equals 2, there's lots of different orbitals. But an electron in the n equals 4 shell, in an orbital somewhere in n equals 4, is higher in energy than an electron somewhere in n equals 2. Now, there's also that the higher number indicates a farther distance from the nucleus, right? So electrons in n equals 4 are farther away from the nucleus than electrons in n equals 2. And this actually relates to the higher energy because there's an attraction between the proton and the electron, and so farther and farther away is higher energy. I don't want to get too deep down that rabbit hole. But, so that is the broadest description, shells. So, as I was saying, higher n equals greater energy and farther distance from the nucleus. So, we can go to the next category, subshell. A subshell is a further subdivision. There are several orbitals in it, but really, one thing the subshell describes is the shape of the orbitals contained in it. So, these letters, these come from some kind of weird, far-out places, like kind of what the spectra looked like on paper when scientists discovered these things. So don't worry too much about where the letters come from, but they're designated S, S, P, D, F. And here's, and I guess I'll talk a little bit more about that. So the number of subshells in each shell is equal to the value of the shell. So n equals 1 only has one subshell in it. And the subshells appear in a particular order, S, P, D, F. Now, so n equals 1 only has one subshell, and it's an S, right? And each shell can only have one subshell. Now, again, in each subshell there is at least one, usually more, orbitals. So n equals 1, that shell only has one single S subshell. N equals 2 has an S and a P. N equals 3 has S, P, and D. N equals 4 has S, P, D, and F. And I'm not going to talk about anymore. You will see why I don't need to go any farther later. But I'm not going to really need to go beyond F. So there's also a little bit of an energy increase in the order of the subshells S, P, D, and F. However, it's not a greater energy increase than the shell itself. So I'm going to draw these a little bit weirdly. I'm going to draw, so the first subshell is, so we have energy 1, and then we have the S in there. And then shell 2, and this is increasing in energy. Subshell S, subshell P. 3, S, P, D, and so on and so forth. So you see within the shells, shell 2 is higher in energy than shell 1, shell 3 is higher in energy than shell 2, and within the shells there's an increase in energy of SPD, right? So here's what I just said. Even though subshells have different energy, the energy differences between shells and subshells between the shells is much larger. Subshells are designated by a number and a letter. So notice I said earlier, so within shell 1 there's an S, and within shell 2 there's an S and a P. So to indicate this orbital, the S in 2, I'd indicate it as 2S. 3S indicates the S subshell in shell 3. 3P indicates the P subshell in shell 3, right? So we get this shorthand notation indicating which subshells we're talking about. So there we go. Finally, orbitals. kind of getting down to the last bit. The orbitals are the actual houses in which the electrons reside. So we have, right, we have shells as our broadest category, shells, and then within shells we have subshells, and then within each subshell we have orbitals. And within the orbitals are electrons. Right? So each orbital, or each shell has multiple subshells, each subshell has multiple orbitals, and each orbital has electrons in it. So, finally getting down to orbitals. So it's that region of space. Several orbitals can be found within a given subshell. Now, each given subshell, S, P, D, and F, no matter which shell it's in, right, always have a different number of electrons. But also, each orbital in a given subshell has the same energy. So, within 2p, all of the orbitals, which I'm going to draw each orbital just as a line, they all have the same energy, right? But that's still higher in energy than 2s, right? Now, the number of the number of orbitals in a subshell is fixed by the type of subshell. So no matter which shell it's in, every s subshell contains one orbital. So 1s contains an orbital, 2s contains an orbital, 3s contains one orbital. P's always contain 3. So 2s contains 3 orbitals, 3s contains 3 orbitals. Think about, so 4s also contains 3, or 4p, I keep saying s. 4p also contains 3 orbitals. 1p doesn't exist. It's important to remember. P doesn't show up until the second shell. D doesn't show up until the third shell, and F doesn't show up until the fourth shell. Now, these just go up by 2, so it's just counting odd numbers. S has 1 orbital, P has 3 orbitals, D has 5 orbitals, and F has 7 orbitals. And finally, kind of getting to the final point here, each orbital can hold 2 electrons. So now we're going to start being able to create a picture of how the electrons are arranged in an atom. Now I should say this. I said that the orbitals, the subshells, S, P, D, F, all describe a particular shape. So all s orbitals are spherical. So they kind of look like this. So this is just the space where an electron spends its time. Now, as you go up, so remember n is the shell, n, 1, n2, n3. So this is 1s, 2s, 3s. They get bigger, but they're still all spherical. Now, remember p orbitals, I said, there are 3 p orbitals in every p subshell. Now, the reason there can be 3 is they all have the same shape, but they're oriented differently. You can't have multiple s's because you can't really orient a sphere any differently, right? You turn a sphere around 180 degrees, it's still a sphere. You turn it 90 degrees, it's still a sphere, right? Well, the p orbitals look like this. They look kind of this weird dumbbell shape, right? So if I now rotate it, now I have a different orbital. Same energy, but it's a different orbital that can accommodate a further 2 electrons. So 2 electrons can live in this one, 2 electrons can live in this one, and 2 electrons can live in this one. So now we have 3 p orbitals that all have the same energy. And just as a quick vocabulary, things having the same energy are degenerate. So all 3 p orbitals are degenerate. Now again, the 3p orbitals, of which there are 3, right, because in a p subshell you have 3 orbitals. In 3p, they have higher energy, but there's still 3 of them, and all 3 of those 3p orbitals have the same energy. We'll show a diagram in a little bit. And the d orbitals, they kind of start looking really wonky, and they are also degenerate, but there's 5 of them, and that's it. Or at least that's it for talking about the orbital shapes. Finally, I need to talk about something called electron spin. So, as I said, you can have 2 electrons in an orbital, right? as electrons are doing whatever it is they're doing in there, I don't know what they're doing, I just know that they're in that space, they have a certain spin, right? They can spin either clockwise or counterclockwise, right? So the electron is either spinning this way or it's spinning this way, right? So each orbital can hold 2 electrons. However, in order for them to exist in the same space, they have to have opposite spin. We're not going to care what the spin of a lone electron is. In fact, a lone electron, an electron hanging out by itself in an orbital, actually spins, it keeps changing direction. It'll go clockwise and counterclockwise for a bit. It just keeps switching direction. What's important is that 2 paired electrons have to have opposite spin. One of them has to go one way, the other has to go the other way. So, kind of backing up and taking everything together, I want to give you a little bit of a picture here. So in shell 1, there is one subshell, the 1s. In 2, there's 2s and 2p. In 3, there's 3s, 3p, and 3d. Now, in these orbitals, or in these subshells, right, each one of these is a subshell. Subshell, 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 subshell. I have 6 subshells drawn here. There are 3 shells. This is a shell, shell, shell. And within each of the subshells are orbitals, and I'm just going to draw each orbital as a flat line. So in S, in every flat line with no thing, there we go. They all have 1 orbital, right? So 1s, 2s, 3s all have 1 orbital each. The p's have 3 orbitals each, right? 1, 2, 3, 1, 2, 3, and D has 1, 2, 3, 4, 5. And in each of these are going to be able to go 2 electrons. 1, 2. So in the first shell, we can only get 2 electrons. In the second shell, I can get 1, 2, 3, 4, 5, 6, 7, 8. Right? So 1, 8, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 2 electrons in the first shell, 8 electrons in the second shell, 18 electrons in the third. Right? So hopefully that gives you a little bit of a picture of what it's looking like. So in the next set of lectures, I'm going to talk about how we actually determine electron configuration.